Hello everyone, it's Angela, and today we're going to be talking about van der Waals gases, otherwise known as real gases. Now, we've talked a lot about ideal gases, and they obey the equation PV equals nRT. If we set the moles to 1, we have PV is equal to RT. By dividing both sides by RT, we will have that PV over RT is equal to 1 for ideal gases. And if we draw this against varying pressures, it will look something like this. This is the ideal gas line with a horizontal line at 1. However, real gases do not look like this, they look like this. Here we have 3 different curves of real gases, and they are all not a straight line, so they cannot be obeying the ideal gas law, and instead they are obeying a new equation called the van der Waals equation, and it is as written: P plus A n squared over V squared multiplied by V minus NB is equal to nRT. Now, there are 2 relatively new constants in this equation, the A constant and the B constant. A constant refers to the attraction between gas molecules. The B constant relates to the size of gas molecules. All gases have their own A and B constant. So I'll show you a table of gases with their A and B constants, in which the gases are the ones found in the graph. Now that we have our table, let's look at the data to see if we can find any patterns. Starting with the A constant. This table is ordered in smallest to largest A constant. So CO2 has the largest attraction between gas molecules, followed by N2, and H2 has the smallest. This can actually be seen in our graph. And before we get into it, let's note that all the curves in this graph are at constant temperature. Now, if we look at the CO2 curve, it has the largest dip compared to N2 and H2, and this corresponds with CO2's large A constant. Because the attraction between gas molecules are so large, the volume is smaller compared to an ideal gas, as well as its pressure. So, this A constant is leading to this large dip, and as they get smaller, so do the dips. Now let's look at the B constant. This table is also ordered in smallest to largest B constant. So CO2 has the largest gas molecules, followed by N2, and then H2. The B constant corresponds to the slope of the curves. So the larger the B constant, the steeper the slope. And now let's go into the 2 regimes of this graph, above and below the ideal gas line. Now, below the ideal gas line, PV over RT is less than 1. In this region, the gas molecules are highly attracted to each other, which is causing for a reduced pressure and volume. That means that this region is controlled by the A constant, as the A constant relates to attraction. Above the ideal gas line, PV over RT is greater than 1. In this region, the volume is actually the volume of the gas molecules themselves. And so the molecules in this region cannot get any closer to each other, so the volume can be considered fixed. Therefore, this region is controlled by the B constant, as it relates to size. Now, that is our video for today. I hope it was helpful in an introduction to van der Waals gases. I hope this was helpful. Thank you so much for watching.